Good morning, students. In last class, we discussed about the power electronic device that are triac, diac. In that, we discussed the construction, operation, and characteristics of triac and diac. Thereafter, we discussed the applications of triac and diac. Today, we'll discuss about the optoelectronic device. That means these electronic devices are related to the light. Opto means light. These optoelectronic device mostly used in the optical fiber communications. Optical communications, we know. Yes. Why we are using optical communication? We know this optical communication, we are sending the information through the light. That means with the light velocity. So this optical communication will provide the higher data speed. Yes. Nowadays we are using all the network cables or optical fibers only. Yes. So in this optical communication, we are using this kind of optoelectronic device. So today we'll discuss about this. Yes, opto means photo electronic device or photo device. So here light is in the form of electromagnetic radiation. We know it is a EM wave. Light is nothing but electromagnetic wave. Yes. So firstly we discuss the electromagnetic spectrum. So in that we are having gamma rays, X rays, UV rays, and visible light, infrared light, microwave, and radio wave. These are the different types of waves based on the its wavelength. Yes, gamma rays generally used in the radiotherapy, and X rays we are using in imaging or X ray. UV rays, these kind of UV rays used in the photolithography, so which is used in IC fabrication. Visible light and infrared light, these two waves are used in the optical fiber communication. So here we are sending the information through these two lights or these two waves, visible light and infrared light. And next, microwaves are used in the wireless communication, like our mobile communication. And radio waves, we are using these in TV broadcasting and radio signal broadcasting. This EM wave is classified based on the wavelength. So the wavelength is more for the radio waves and wavelength is less for the gamma rays. So that wavelength and frequency is inversely proportional. Inversely proportional. Yes. So this is about the electromagnetic spectrum. So in this we are discussing about the visible light and infrared light. Why? Because these two are used in the optical fiber communication. So we are discussing about the optoelectronic device. So that optoelectronic device will generate the light which is related to the visible light and infrared light wavelength. Yes, We know human can detect only visible light. Yes, so it can detect if the photon wavelength is about 4000 angstrom to 7000 or 8000 angstroms. Yes, if the photon wavelength is not in the range of 4000 angstrom to 8000 angstroms, we cannot detect, our human cannot detect. Yes, so such photon radiation is called visible light. Yes, human can detect only 4000 angstrom to 8000 angstroms, or you can say zero point 0.4 micrometer to zero point 0.7 or zero point 0.8 micrometer wavelength of photon radiation only detected by the human. The other wavelengths we cannot detect. So such range of wavelength is called visible light. Infrared light is called, it is invisible light because human cannot detect. So generally infrared wavelength is about zero point 0.9 micrometer. So our range is only 0.4 to zero point 0.8 or zero point 0.7, but infrared is 0 0.9, so we cannot detect the infrared light. Yes, so infrared is invisible light. Mention the wavelength of the different waves, and its energy is can be calculated by using the formula E equals to 1.24 by lambda, which is in the micrometer. Yes, so ultraviolet UV rays, the wavelength is generally varies from 0.315 to 0.38. So violet and indigo, these two are colors indicated in the 0.38 to 0.45. For the blue color, it is 0.45 to 0.495, and green 0.495 to 0.57, yellow 0.57 to 0.59, orange 0.59 to 0.662, red 0.6 to 0.75, infrared 0.75 to 1.94. Yes, this is about the wavelength of the each color. So human can have the maximum response to photon wavelength of only 0.55 micrometer. So it is about only up to green color, green light only. Yes, so this is about the wavelength of the each color. Types of the photo device or opto device. These photo devices are basically classified in two types. One is light source, another one is light detector. In optical fiber communication, we are sending the information through the light. Yes, so that means that photo device we are using as a source. That means we need to convert the electrical signal into light. So that are light source. So generally we are having the information in electrical signal. We need to send that electrical signal through the optical fiber, but optical fiber is working with only light, so we need to convert that electrical signal into the light. So we are having the source, that is light source. Here we are using the LED light emitting diode as light source, which is used to convert the electrical signal into the light. Similarly, laser diode, it is also light source. It is also used to convert the electrical signal into the light. So now that light is passing through the optical fibers. After the reaching to the destination, that means destination point, we need to detect that light, and we need to convert that light into again our electrical signal. Yes, so at the receiving end, we are using the light detectors. That light detectors are used to convert the light into the electrical signal. So that device are photodiode, pin diode, avalanche photodiode, and solar cells. So in optical fiber communication, so in general any communication we are having, the one is transmitting and another one is receiving end, and transmitting end is used to transmit the information and receiving end is used to receive the information. In between we are having the medium. Here the medium is optical communication. So this optical medium, that is nothing but optical fibers. So these optical fibers are allows only information in the form of light. So we are having the information in the form of electrical signal. So we need to convert that electrical signal into light by using the light source. In that we can use either it is a LED, either it is a laser. So by converting the electrical signal into light by using LED or laser, that signal is transmitted through the optical fibers. At the receiving end, we need to convert that light into the again electric signal. So that can be done by the either it is a photodiode or pin diode or avalanche diode or solar cells. These are the two major photo device. One is light source, another one is light detector. This light source is used to convert the electrical signal into the light, and light detector is used to convert the light to electrical signal. And third one we are having the optocoupler. It's a combination of LED and photodiode or LED and phototransistor fabricated in a single package. These are used for the electrical isolation. These are used for the electrical isolation. So firstly we'll discuss about the light source. In that we discuss the LED. It's nothing but light emitting diode. So diode, we know, we already discussed about the different types of p junction diodes. Yes. So we know the normal p junction diode. Here it is also LED light emitting diode. It is also diode, but it emits the light. Yes. So it is a two terminal device. It is also a PN junction diode, but it is fabricated from the direct band gap semiconductors. So we are not classify this direct band gap and indirect band gap semiconductors in the earlier lecture. So this will be discussed in the next class. So generally this direct band gap and indirect band gap semiconductors are the two types. In this direct band gap semiconductors, here the a free electron present in the conduction band can directly recombine with the holes present in the valency band. So whatever the electron present in the conduction band, that will be directly recombined with the hole in the valency band. This is called direct recombination. We know. Yes. So when an electron returns to a valency band, energy will be released in the form of photons or light particles. So therefore direct recombination is also called as radiative recombination. So direct band gap is nothing but what are the electron present in the conduction band, that will be directly recombined with the hole in the valency band. These kind of semiconductors are direct band gap semiconductors. So in this the electron is directly recombined with the hole present in the valency band. So that electron is not changing its momentum. So the momentum of the electron is same at the any point. So these semiconductors are called direct band gap semiconductors. These direct band gap semiconductors are gallium arsenide, gallium phosphate, and gallium arsenide phosphate. These are the examples of the direct band gap semiconductors. These direct band gap semiconductors are generally used in the LED fabrication. Why? Because so the electron present in the conduction band is directly recombined with the hole present in the valency band. In this duration, energy will be released in the form of photons. Whatever the released energy in the form of photon, it is nothing but light. Yes, this light will be emitted in the this p-n junction diode. Yes, that's why we are calling it as a light emitting diode. So these direct band gap semiconductors are used to fabricate the light emitting diodes. So in normal p-n junction diode, we are using the indirect band gap semiconductors. In that indirect band gap semiconductors, free electron present in the conduction band is not directly recombined with the hole present in the valency band. Here or in the indirect semiconductors, the recombination takes place in two steps process. First, the free electron moves into the some intermediate level by changing its momentum and energy. Then after, electron will move from intermediate level to the valency band and it will recombine. So in indirect band semiconductors, the free electron is not directly recombined with the hole in the valency band. Initially, it is moving into the conduction band to the intermediate energy level by changing its momentum and energy. Then after, again, that electron will move from intermediate level to the hole that intermediate level to the valency band and it will recombine with the hole in the valency band. So here the momentum of the electron is different values for the different energy levels. That means the momentum of the electron is varies with the different energy levels. So the momentum of the electron is not same in all the points in the recombination process. Clear? So the examples for the indirect band gap semiconductors are the silicon and germanium. So when the electron from the conduction band to intermediate level to valency band, then it will recombine with the hole in the valency band. In this process also it will release the some energy, but the released energy in the form of photons. So these photons are, we can say, it is nothing but energy in the form of heat. So in the indirect band gap semiconductors, we can get the energy in the form of heat. In the direct band gap semiconductors, we can get the energy in the form of light. Clear? That's why we are fabricating the light emitting diode by using the direct band gap semiconductors. So this LED operation is also is also similar to the normal p-n junction diode. So LED is also operated in the forward bias. Visible light LEDs are fabricated from the direct band gap semiconductors whose energy gap is lies between the 1.75 electron volt to or 3 electron volt. So whatever the energy gap of direct band gap semiconductor is always equal to the released energy released e- energy released photon energy. Yes, the energy gap of the band gap semiconductor is always equal to the released photon energy. So these visible light LEDs are always fabricated from the direct band gap whose energy band gap is always lies between the 1.75 electron volt to the 3.2 electron volt, and it is also equal to the 1.8 to 3.2 volts. So this is the voltage drop of the visible light LEDs. Yes, in normal p-n junction diodes, we are having the voltage drop is zero point 0.7 or zero point 0.8 volts forward voltage drop. So coming to the visible light LEDs, we are having the 1.8 to 3.2 volts. So the cutting voltage of visible light LED is 1.8 to 3.2 volts. Some of the materials, semiconductor materials, are used to fabricate the LEDs. So here we mentioned some of the materials. One is gallium phosphide. So it has the energy gap of 2.2 electron volt, which correspond to the wavelength of 0.54 micrometers. This 0.54 micrometer wavelength is indicates the wavelength of green. Yes. So this gallium phosphide material energy gap is 2.26 electron volt. Yes. So 2.26 electron volt energy gap. So we know energy equals to 1.24 by lambda. So lambda equals to 1.24 by energy gap. We will get the 0.54 micrometer. This 0.54 micrometer wavelength indicates the green color. So when you are fabricating the PN diode by using the gallium phosphide material, then it will emit the green light. So it will act as a green LED, green light emitting diode. And gallium arsenic phosphide, it is also a direct band gap material whose energy gap is varied by changing the composition of phosphorus arsenic values. So it is useful in fabrication of LEDs, so which can emit the yellow and orange and red light. So here gallium arsenic phosphide, the the composition is gallium arsenide phosphide. Here gallium arsenide 1 minus x 1 minus x and px, where x is nothing but mole fraction. This x indicates the mole fraction of phosphorus and arsenic value. This phosphorus and arsenic changing its mole fraction value, it will emit the different types of colors. Either it is a yellow color, or it is a orange color, or it is a red color. So this gallium arsenic phosphide can be varied from the 0 to can be used as a yellow LED or orange LED or red LED by changing its X value. Yes, generally this X value is always greater than the is always lies between the 0 to 0.45 according to its energy gap will be varied. When the mole fraction of the phosphorus and arsenic varies, then energy gap of the material will be changes. So based on that energy gap, that PN diode will act as either it is a yellow LED or orange LED or red color LEDs. Yes. So next, gallium nitrate. So it is also one of the direct band gap material. So here the energy gap of this material is 2.6 electron volt, which corresponds to the wavelength is 0.47 micrometer. Hence, it is used in the fabrication of blue color LED. Infrared LEDs are also fabricated from the direct band gap materials whose energy gap is 1.24 electron volt to 1.65 electron volt. Next, gallium arsenide, which has the energy gap of 1.42 electron volt, it is used in the fabrication of IR LED. So here gallium arsenide energy gap is 1.42 electron volt. So it will generate the wavelength of infrared rays. So this can be used in the IR LED fabrication. Operation of LED. So it is like our normal PN diode only. So here the P-N junction is fabricated by using the direct band gap semiconductors. So we know when LED is operating in the forward bias, holes are injected into the N region and electrons are injected in the P region. That means Electrons present in the conduction band, holes present in the valence band. Conduction band of n region, electrons in the conduction band of n region, electrons are moving from conduction band to holes valence band in the p region. So here these electrons will recombine with the holes. So in this recombination process, what happens? So it's nothing but a direct recombination. Why? Because it is a direct band of materials. So in this direct recombination, energy will be released in the form of photons or light. Yes, that energy is, we know it is equals to h into f, or h into c by lambda. Yes, so that lambda is the wavelength. So that wavelength indicates the type of color, or type of wave, either it is a red color or orange color or green color light. So this emission of photon when electrons from conduction band returns to the valence band on its own is known as spontaneous emission. So here you can observe in the diagram. So when the electrons are moving from the conduction band to valence band, it will release the energy in the form of photons. It is nothing but h into f, or it is nothing but h into c by lambda. So here lambda is the wavelength of the light. So here LEDs have the spontaneous emission. You can observe the symbol of the LED. So it is looking like a normal PN diode, but it emits the light. So on top here indicates the arrow marks outside, it indicates the light emitting, and it is connected in the forward bias. So when it is connected in the forward bias, then what happens? So holes are moving from the p region to n region. Electrons are moving from the n region to p region. So in this direct recombination process, so photons will be released. So that photon in the form of light. So that light will be depends on the wavelength. So this release energy is always equals to the band gap of material, energy band gap of material. So here we can observe the forward voltage drop VD, and R is currently being registered. So it is used to avoid the damage of LED. Yes. So this forward voltage drop is generally 1.8 to 3.2 or 3.6 volts in the LEDs. Coming to the normal penetration rate, this forward voltage drop is 0.3 to 0.3 to 0.7 volts. So these LEDs have the higher forward voltage drop, that means higher cutting voltage. So they operate at higher currents. So from this we can write the current flowing in this circuit. We can write I equals to V minus Vd by R. So I equals to V is nothing but applied voltage, Vd is the voltage drop, forward voltage drop, R is the current limiting resistor. So here this current is always directly proportional to the applied voltage, and the light intensity is also always directly proportional to the applied input voltage. Otherwise we can say the intensity of light is directly proportional to the forward current or applied voltage. These these LEDs are converting the electrical signal into the light. So from that we can say optical conversion efficiency of LED is nothing but it's the ratio of optical power to the electrical input power. It is the ratio of optical power to the electrical input power. So the characteristics of these light emitting diodes is similar to the normal p junction diode, but the cutting voltage of the forward voltage drop is more in the LEDs. And coming to the reverse bias, it is like a normal p junction diode only. The reverse bias is it works as normal p junction diode, but in forward bias it emits the light. The forward voltage drop is more compared to the normal PN diodes. So normal PN diodes are fabricated by using the indirect bandgap semiconductors like germanium, silicon. So in this recombination also we are having the energy in the form energy, but it is in the form of heat. But coming to the direct bandgap semiconductors, we are having the energy in the form of light. So these direct bandgap semiconductors are used in the LEDs. These LEDs have the spontaneous emission, so in which the released energy is always greater than or equals to the energy gap. As a result, photons released may not have the same wavelength. So this light this emitted light is not a monochromatic here. Clear? So it is a coherent. Problem we can solve here. An LED is fabricated using direct band gap material having the EZ equals to 2.5 electron volt. What is emission wavelength of radiation? Second one, if LED carries a forward current of 10 milliampere with 2 volts forward drop and its optical conversion efficiency is 20%, then calculate number of photons emitted per second. So here the given data is energy gap is 2.5 electron volt. So we can calculate the wavelength. So we know lambda equals to 1.24 by energy gap in the form of electron volt. The result will be in the form of micrometers. So it is nothing but 1.24 by 2.5. It is nothing but 0.496 micrometers. So 0.496 micrometer wavelength. Clear? So this 0.496 micrometer wavelength is indicates green color as green LED. Yes. And second one is if LED carries a forward current of 10 milliamperes, so I equals to 10 milliampere with forward voltage drop VD equals to 2 volts and its optical conversion efficiency equals to 20%. So efficiency equals 20% is nothing but optical power to the electrical input power. So we need to calculate the number of photons emitted per second. So here we are having the current and forward voltage drop. So we can calculate the electrical input power. So we can write Pi equals to voltage drop, forward voltage drop into current I. So we can write 2 into 10 milliamperes, it is equals to 20 milliwatt. So electrical input power equals to 20 milliwatt. So efficiency equals to, we can write optical power to the electrical input power. So it is equals to 20%, we can write it is equals to 0.2. From that we can write optical power equals to input power into efficiency. So 0.2 into Pi. So 0.2 into 20 milliwatts, we can write it is equals to 4 milli. Sorry, it is a 4 milliwatt. So here units mentioned is a volts, but it is a watt. So optical power is 4 milliwatt. So we can calculate the number of photons emitted per second. So optical power can be written as number of photons emitted per second into energy of each photon. So we can write number of photons emitted per second equals to total optical power by energy of one photon or each photon. So we can write optical power equals to 4 milliwatt, it is equals to 4 into 10 power minus 3, and energy of one photon equals to, so one photon is the energy of one photon is nothing but we can write energy gap of material. Yes, it's nothing but 2.5 electron volt, and we need to write in the joules. So it is multiplied with the 1.6 into 10 power minus 19. So 4 into 10 power minus 3 by 2.5 into 1.6 into 10 power minus 19. From that we can write it is 10 power 6 photons per second. So it will emits the 10 power 6 10 lakh photons per second. So in 1 second it will emit the 10 lakh photons. Yes, this is about the light emitting diodes. Next we will discuss about the laser diodes. Thank you.